Let matrix M is given by this matrix, and if B equal to this matrix where x1, x2, x3, this column vector y1, y2, y3 and z1, z2, z3 are linearly independent eigenvectors of M, then the main diagonal of the matrix M of the matrix B inverse MB has, means we have to tell about the diagonal entries of B inverse MB. B inverse MB means we do not need to tell about the exact diagonal elements, because in a matrix elements are fixed. So diagonal entry may be like this. So we can't say about this entry is here, here, and what will come here at these three places. What from what values these entries should be chosen, we can tell about. If you focus on matrix M, then you can easily check this is diagonal elements and all diagonal elements are real, and you can see that this one entry are conjugate transpose. You can see this one also and this one also. So matrix M is nothing but Hermitian matrix, and we know that a Hermitian matrix has real eigenvalues. So all eigenvalues of M is real, and by this property B inverse MB, B is non-singular matrix because B inverse is in pre-multiplication. So you can see matrix B is are coming by linearly independent eigenvectors of M. So this matrix, because of linearly independent, you can say that in terms of rank of this matrix B is equal to 3, or you can say determinant of B is non-zero. So determinant is non-zero, so inverse exists here, and this is the condition of diagonalizability. So matrix M is diagonalizable, and in diagonalizable matrix, eigenvalues comes at diagonal places, and we know that all eigenvalue will be real of M. So you can say that suppose 3, 2, 1 are eigenvalue. I am not saying that one will here, one will come here, 2 here and 3 here, but we know the value at these three places will come from these eigenvalues only. So exactly 3 real entries. Option C is right. Let P equal to this matrix, then the eigenvector corresponding to the eigenvalue iota and minus iota are respectively. Matrix P is given, and we have to tell about eigenvalue of eigenvector corresponding to eigen. Suppose this is V1, this is corresponding to eigenvalue 1, and this is V2, this is coming corresponding to eigenvalue minus iota. To find eigenvalues P minus lambda I, we need to compute determinants of this matrix equal to 0, and this will give us characteristic polynomial. So P minus lambda I, or in terms of x, you can say that this one x1, x2 should be equal to 0. Now lambda I, it means P is 0, 1 minus 1, 0. Subtract this matrix lambda lambda 0, 0. We will obtain P minus lambda I. it will be minus lambda because lambda is given iota, so you can directly put iota here. So iota or minus iota minus 1, 1 and minus iota. This is the matrix x1 x2 will equal to 0 corresponding to eigenvalue lambda I is, or lambda 1 you can say, iota. It means this implies minus iota x1 plus x2 equal to 0. Now from option A, B, C or D, because we are seeking eigenvector corresponding to eigenvalue iota, so either you can choose second position or second element of the vector, column vector, or first element. So if I choose x2 equal to, or value of x1 is 1, value of x1 as in option A, and in option B value of x1 is 1. If 1 is true, then we can A and B be possibility. Now check which one is most probably possible option. Put, you can find x2 equal to iota x1, value of x1 is, put x1 equal to 1, then x1 x2 will be, value of x1 is 1, so 1 here, and value of x2 will be iota. So 1 and 1 iota, this vector will be the eigenvector corresponding to eigenvalue iota. So 1 and iota is coming in option A and B. So other two options will discard here. If I choose eigenvalue minus 1, sorry, first element minus 1, it means x1 is minus 1 as in option C. So you can see x2 equal to iota times x1. So value of x1 is iota, then this one will be minus 1. So I choose iota, and this one we are getting minus 1. So option C discard here, because minus 1 you can check here, we are getting this element. Similarly, by putting iota you can check option D will be discard. So by putting first element or second element of a constituent of a matrix, sorry, of a constituent of the vector, then you can easily discard option here. So correct choice is, or most possibility is this one. So corresponding to eigenvalue iota, eigenvector is 1 iota. Now we are seeking eigenvector corresponding to eigenvalue minus iota. For minus iota, we need to find eigenvector corresponding to this one. So let, similarly x3, x4 is eigenvector corresponding to this eigenvalue. If this is eigenvector, then P minus, or because of this, you can say P plus iota identity matrix x3, x4 will be 0 vector of correct size. So we will obtain P is 0 minus 1 1 0, P is 0 minus 1 1 0. This is matrix P. So this one will be iota minus 1 1 and at this position 0. And this is matrix, this is column vector x3 x4. This is eigenvector 0 0 as this is now calculation part. Multiply by I r2. We are changing r2 by r2 minus r1, and we cannot multiply like this. So you can divide here, and you need to make this entry 0. So multiply first row r2. How we are applying elementary row operation of on this matrix r2 plus iota r1, because this element is iota, so iota multiplied by iota will give you minus 1, and this is also minus 1, so need to subtract this. So minus 1 and this negative turns it to positive. So we will obtain a matrix iota 1 0 0, and this is x3 x4, and this is equal to 0 0. We are getting iota x3 plus x4 is equal to 0. It means iota x3 equal to minus x4. Now choose any value. As in option, you can see what is the first constituent or second constituent. You can see either you can choose first or second constituent of elements as minus 1 iota, iota, minus iota, anyone, and that will confirm you or verify which one is true. If I choose x3 is equal to or x4, you can say easily iota, then x3 x4 will be minus 1 iota. Now this is the vector in option A, so option A is the right choice here. Now come to the next question. Let P be a 2 by 2 matrix such that P raised to the power 102 is equal to 0. Then which one option is true here? As size of the matrix is 2 by 2 means a square matrix. Also P raised to the power 102 is equal to 0. Any positive integral power of any matrix is giving 0, then this is nilpotent matrix. Nilpotent matrix. But this may not be, maybe or may not be, may or may not be order of nilpotency. Order of nilpotency. But also order of nilpotency, order of nilpotency never exceed size of the matrix. Size of the matrix. Here size of the matrix is 2. So order of nilpotent, this nilpotent matrix never exceed by 2. So order of this matrix is 2, because P, if order of this matrix P is 1, then P is 102 is 0 matrix. P is nothing, 0 matrix. So order of this nilpotent matrix is 2. So option A is true here. Also you can verify this by taking any matrix like this is the matrix of size 2 by 2 and p raised to the power 102 will give you 0. So hypothesis condition or hypothesis satisfy here. So you can check that p square is 0. So option A verify. This is by trial and error. Let P be an n by n idempotent matrix. Idempotent matrix, the definition is P square is equal to P. Which of the following is false? P transpose is idempotent. The possible eigenvalue of P are 0 or 1. The non-diagonal entries of P can be 0. There are infinite number of n by n non-singular matrices that are idempotent. For option A, we need to check transpose, P transpose is idempotent or not. We say a matrix is idempotent if its square is equal to itself. If we need to test P transpose is idempotent or not, so its square will should give P transpose. Now consider this left hand side. P transpose square is nothing but P transpose P transpose, and this is PP transpose. We can write this one, and this is P square transpose, and P square is P as by given condition. So P transpose, and we obtain this condition. So P transpose is idempotent. Option A is true here. Now you can verify this by alternate as P square is equal to P and P is n by n matrix. P is n by n matrix. If P inverse exists, I am saying if P inverse exists, then multiply by P inverse. P inverse P square equal to P inverse P by pre multiply. This will give you P equal to identity. So this is means infinite number infinite number of n by n, because of P is nothing but identity matrix, and we know identity matrix we can obtain any size. So there are infinite n by n identity matrix, and identity matrix are non-singular that are idempotent, because identity raised to the power n will give you same matrix. So there are infinite number of n by n matrix that are idempotent, and this condition is only true when P is non-singular. This condition should be given here. So option D is not right, because we are seeking false statement here. Option A is true, option D is not true, as non-singular. There are infinite number of n by n non-singular, and we are getting P is nothing but identity matrix. So we have many identity matrix of this size, but we have nothing about identity matrix. So by the word infinite, there are infinite number of n by n non-singular matrices that are idempotent, this statement is false. Now come to the question. If P equal to this matrix, then P has two linearly independent eigenvectors. P has an eigenvector. P is non-singular. There exists a non-singular matrix S such that S inverse PS is diagonal matrix. Now matrix P, this is matrix P, and you can say that you can see that matrix P is symmetric matrix. Symmetric matrix because this is element is same if for option D you can say diagonal matrix. For diagonal matrix, this condition should be true. Algebraic multiplicity of lambda I should be equal to geometric multiplicity of each lambda. This is the condition for diagonal matrix. Matrix P is given 1 iota minus 1. To find its eigenvalue, we need to find P minus lambda I equal to 0. Now consider lambda I 0 0 and subtract this one. So this will be P minus lambda I matrix. It will give us 1 minus lambda, and this is minus 1 minus lambda, and other entry is same as iota. This is 1, and we need to find determinant of this matrix to find eigenvalues. So its determinant will be 1 plus lambda, or 1 minus lambda, minus iota square means minus 1, so plus 1 will be 0. It means minus of 1 square minus lambda square plus 1 equal to 0. It means this implies 1 minus lambda square equal to 1. So lambda square is 0. So lambda equal to 0 0. Here there are two repeating eigenvalue. So not distinct eigenvalue, so implies not diagonalizable. If distinct eigenvalue, then compulsory is diagonalizable. If this is, we are saying by negation, so there exists a non-singular matrix S such that S inverse P S is a diagonal matrix. This is the condition for diagonalizability. So matrix P is not diagonalizable, so option D discard here. P has two linearly independent eigenvectors. To find eigenvector corresponding to eigenvalue 0, we need to find P minus lambda is 0. So 0 into identity matrix will be same. So this is only matrix P with vector, consider x1 x2 is 0 0. Means P is 1 iota, this is also iota, and this is minus 1, and this one is x1 x2 equal to 0 0. Now solve there here calculation part only. So x1 plus x2 iota x2 equal to 0 by, we are changing r2 by minus r1. By this elementary operation, we will get this matrix 1 iota 0 0 x1 x2 equal to 0 0 of correct size. So we obtained this condition x1 plus iota x1 plus iota x2 equal to 0. Now put any value of x2. Suppose x2 is x1 is minus of x2. If you put value of x2 is 1, then value of x1 will be minus iota, and this is x1 x2 means eigenvector. So there is only one eigenvector, only one eigenvector corresponding to eigenvector 0, because we have only one eigenvector. Li eigenvector means its geometric multiplicity is 1, but algebraic multiplicity of lambda equal to 0 is 2. Algebraic multiplicity is not same as geometric multiplicity. So option A discard here, because saying two linearly independent eigenvectors and we obtained only one eigenvector. P has n eigenvector. So this will be true. P is non-singular because one eigenvalue is 0. So P will not be singular. So sorry, non-singular, because product of eigenvalues gives determinant and its determinant will be 0. So P is not non-singular. So this one is also false statement. So true statement is only B.